right here, this is the general form of, for this one, it would be a sine. If you had a cosine there, then it wouldn't change anything except basically it just shifts the same graph to a different position, right? And here it's talking about what each thing means. A is the amplitude, omega is the angular frequency, and theta is the phase shift. Now, also, the time shift, which is something that we haven't gotten from here. So remember, if you watch the video, the general videos on graphing, I said if you have if you have a shifted form, well, and this is a shift, this plus theta is a shift. What you really want to do is factor out the omega. So we would have sine of, and I'm going to factor out omega. That becomes t. When I factor omega out, basically I divide both of these things by omega. So this would be t plus theta over omega. Okay? And as I've said before, this is our amplitude. This is our angular frequency, as it says, angular frequency. And now, instead of it being called our phase angle, this is called our time shift, which is basically our horizontal shift. So if you want to know how much you're going to shift something to the right or to the left, you would look at that number after you factor out that omega. Okay. All right. So now let's do this problem. Hold on. Okay. So consider a cart of mass m moving on frictionless rollers as shown here. They're just saying frictionless because otherwise we'd have to add something else in. The mass is attached to the end of a spring of stiffness K. So harmonic motion of a spring mass system. Suppose that the position of the mass V of t is given by this equation. Now we're getting to a different equation. I told you what each thing means, but now we're going to talk about it a little differently. So suppose that this is our equation. Determine the amplitude, angular frequency, period, phase angle, and time shift. Okay. And we have our hint there. So A, our amplitude here is 2. That's our amplitude. I'll change colors for everything out of that. Our angular frequency, which is our omega, is equal to 6 pi. Our period is equal to 2 pi over, so remember, I have to divide by our omega over 6 pi. So our period is 1/3. Our phase angle, so that's our theta, is our phase angle. And I didn't change color, I said I would. Our phase angle, theta, is pi over 2. And our time shift, I'll get another color. What color do we want to use here? So I use red, blue. This was all supposed to be in green. Actually, let me just change it to green. So our phase angle is theta, which equals, so we'll do that. And then let me get one more color. Let me choose black. And our time shift is equal to theta over omega, which is pi over 2 over 6 pi. I'm going to simplify this fraction. However you do it, you're going to get the same thing as I am. Basically, this is 2 times 6 pi. Pi's cancel, and I get 1/12. So 1/12 is my time shift. Okay. Now, it says for B, let me line there and do B. Okay, so B says find X of 2 seconds. Which is, this is X of T, so basically at T equals 2. And I have the whole equation, so I can just say X of 2 is equal to 2 times the sine of 2 times, here, I'll write it out, 6 pi times 2 plus pi over 2. So this is 2 times the sine of 12 pi plus pi over 2. Well, if you remember coterminal angles, if I have 12 pi plus something, so 12 pi plus pi over 2, remember that on my unit circle, if I start here and I go around the circle one time, I have 2 pi. So every two pi, I'm going around the circle a full cycle. So 12 pi really is 6 times around the circle, but I'll end up back at 0. So I don't really care. I can rewrite this as the sine of pi over 2. Because the 12 pi just kind of circles back around over and over again. And then the last piece makes it go to pi over 2. And the sine of pi over 2 is equal to 1. So this ends up equaling 2 times 1, which equals 2. So that is how you do B, or number 2.